Okay.
Okay.
Cool.
I guess I'll give an intro. That's how this works, right? So I'm kind of honored and I'm really excited to introduce Rohan for his thesis defense. Rohan's been one of these students with just an incredible amount of energy, and he's constantly reinventing himself, which I think is just kind of amazing and something I really respect about him as a student. He came in from Berkeley, actually working with Ludwig on sort of just some really cool work on sort of robustness and empirical aspects of that machine learning models. And he came and, you know, it was COVID and we were meeting over at Nora Soups, I remember.
Nora Soups.
And yeah, good times. And I remember Rohan saying, like, I want to do something different. I want to work on like performative prediction and like socio-technical feedback loops. And I was like, what? And then so we worked on this like data feedback thing. And afterwards, you're like, oh, that's cool. Now what are you going to do? And you're like, oh, I want to work on language models and scaling and, you know, democratizing access to AI. And now you're sort of thinking about like multimodality in video. And so I'm just sort of incredibly impressed at the breadth of sort of thought and sort of different areas that he's worked in. And it's the thesis will cover some of it, but there's also some other stuff it will cover, like his really thoughtful, what's they call it, reading group in like philosophy of science. And, you know, Rohan's a lot more broad than even this thesis sort of will show him at. So take it away, Rohan.
Cool. Yeah, thank you for that great introduction. I'm super excited to be here to present some of the work that I've done during my PhD. So yeah, let's get into it. So the title of this talk is Ingredients for Accessible and Sustainable Language Models. So, you know, this doesn't need to be said, but, you know, LLMs are seeing really broad adoption nowadays. For me, primarily, I use it a lot for mostly coding, but there are a lot of applications in writing and marketing, and even more kind of serious applications like medicine and law. And, you know, as we start to deploy AI in more high stakes applications, it becomes important to really consider, to really understand the full pipeline of how we actually train and develop these models. Unfortunately, a lot of this understanding is lacking today, and it certainly was a couple of years ago. You know, in the industry, there's a lot of focus on compute and scale, delivering a lot of the gains. But the details, even the ones that are developed in industry, are not really widely shared. And this has kind of led to a lack of a reproducible pipeline that we can understand and analyze. And I really like this quote from Percy. You know, just a short little rant on, you know, OpenAI is apparently one of their, at the time, you know, this is like November 2022, but at the time, one of the most prominent models was actually based on a code model. And we had all thought it was trained from scratch. So this just kind of goes to show like the lack of understanding and the lack of insight that we really had at the time. Now, when I started working on language models a couple of years ago, this was like a little bit all funny to me because I had come from the vision side. And in like vision land, you know, this is ML in 2010s, things are actually very simple. So the goal was like you set out to solve some specific task. You would go ahead and manually collect and label your data set. And then you would train your models and report performance. So for example, specifically for ImageNet, which was like the de facto benchmark at the time, the authors downloaded some images from Flickr, use crowd workers to label them, you know, truck, shark, dog, and then you would train your model and report your test set performance. And this actually led to a really tight development loop. And this made things really easy to understand. So for example, if you had a new algorithmic change or proposal, you could very easily benchmark it against baselines, you know, compute the proper ablations. And then, you know, you could, you know, be certain that like you were actually making improvement, and this could be widely shared. And it was easy to see, you know, for the rest of the scientific community that like these are the pieces of knowledge that from which we made progress. And this progress is pretty evident. So this is kind of like error rate on the benchmark over time. Undoubtedly, a lot of this was driven by compute and scale, but understanding these smaller technical pieces really allowed us to figure out where to put that compute and scale and how to drive those gains. Now, back in the LLM land, you know, these LLMs in 2020s, things look very different. We sort of moved on from task-specific models to building these general-purpose models. And as such, the pipeline has scaled in complexity and in size. So we start, you know, with a scrape of the internet to train what is called like a base pre-trained model. Then we sort of curate data specific for this model and ask workers to rate and create these responses that then goes to further fine-tune the model and then is finally deployed to the user. So there's a few new challenges in this new pipeline. One, we move away from sort of model independent to model dependent data pipelines. These means that like the crowd workers that we asked to rate these samples are actually dependent on each model. So every new model iteration, we kind of have to go through this process again of creating these data sets. Second, these evals depend on users. It's no longer a specific held out test set that everyone kind of recognizes. But some users might care about coding, some users might care about factuality, some users might care about how well it can recall specific scientific information. So all of these constituents are kind of really hard to reason about. And finally, there's one even more insidious feature or bug, how you call it, that is the hardest to reason about, which is that the internet is a constantly updating data source. And when we deploy these models, and especially as they start to rise in use and popularity, a lot of their interactions are actually stored online. And so this begs the question, how do we reason about the internet as this evolving data source when part of this data is actually a result of model deployments that have happened in the past or currently happening? So all of this kind of begs the question, how do we reliably study language modeling science? And this is the core question that I'll address in today's talk. So I'm going to do this in two ways. And the first is, how do we make training and evaluation more accessible through the use of synthetic data? So let's start with that. Cool. So again, yeah, this is the sort of the primer and the LLM pipeline. I would roughly break this down into 3 stages. I mean, you can dice this many ways, but roughly there's a pre-training stage where you train the model on sort of broad documents on the internet. Then there's a post-training stage where you kind of generate responses from the model and further fine-tune it so it kind of follows user instructions and it feels like a good assistant chatbot. And finally, there's an evaluations phase. And for this section, I'm really going to focus on the post-training and evals phases. Though most of the compute actually goes into the pre-training phase, the pre-trained model is actually kind of hard to deal with, and it's hard to play around with. And so there's a lot of work needed to be done in post-training evals to make this a useful. So for the rest of the section, we'll kind of use like the Llama 7B, which is a pre-trained model from Meta, as a placeholder for the discussion to talk about. So just an illustration of what I'm talking about. So let's take the base Llama 7B, and let's just ask it a very simple question. Make a list of the most popular podcasts. So it gives you something like this. Create a list of variables, process the list of the most popular podcasts, process the data, create a list of the podcasts, make a list of the months. It's a little bit confusing. Like, it's not really clear if the model thinks it should be writing code or giving me suggestions. It kind of looks like pseudocode, but not really. It repeats itself a lot, and it's kind of hard to read. There's a lot of formatting issues, and it repeats itself. Okay, so how do we solve this? So if we look at OpenAI's blog post, this is one of their initial blog posts on Instruct GPT for how they actually created a family of these instruction following models. They outline roughly 3 steps to how to fix this behavior. And so all of this looks a little bit complicated, but the goal of this section is really to break down all these pieces and really understand what are the key bits needed to make this work. So step 1 here, it says collect demonstration data and train a supervised policy. So okay, so that seems like a good start. Why don't we start with step 1? Like what is the most basic thing we can do to get step 1 running so that we can actually fine-tune our pre-trained model. So actually in this step, if you see, it says that we need a data set of question-answer pairs. And this data set is written by humans. Now, as academics, we're on a limited budget. We don't have that much time to either manually write these data sets or pay for CrowdWorks to do so. So what's the next best thing? Well, we already have pretty powerful LLMs available. So why not simply ask the LLM, one of these available LLMs, to generate more examples? That's kind of exactly what we did. So we started with 175 of these seed tasks, which are manually written question-answer pairs. And then we simply prompted TextDaVinci 3, which was the best model at the time, to automatically generate new question-answer pairs given a few of these in context. And we applied this multiple times, and we kind of bootstrapped together a data set of about 52,000 question-answer pairs. And you can see some examples of what this looks like down below. And once we had this data set of question-answer pairs, we supervised, just regular supervised fine-tuned our model, and then ended up with Alpaca 7B. And yeah, so the cost at the time, was $500 on the API. I mean, by now the price has dropped like by orders of magnitude. This is probably a lot cheaper. Okay, so let's go back to our original kind of question. If we ask this instruction tune model, make a list of the most popular podcasts, it kind of tells us right away. This American Life, Serial Town, S-Town, Free Economics. So I don't know if this is like factually correct in terms of like the right list, but at least, it gives us an actual suggestion. It doesn't repeat, it's easy to understand. This is like kind of what we know to expect from instruction following models these days. Okay, so that's great. We sort of like demystified at least step one, and it seems like just having a pretty small data set of these auto-generated question answer pairs can do most of the job. What about step two? There's a lot of talk made of RLHF and its supposed how can improve LLM performance. So let's try and like really figure that out. What's going on here, and how much of this is actually needed. So so it's a little bit complex. So let's just start with like what kind of the traditional pipeline is for doing steps 2 and 3, and then we can talk about how what are the challenges and how we can overcome them. So the typical pipeline is you start with your pre-trained supervised fine-tuned model from step 1. You then ask the model to generate a pair of responses for every new instruction. Human annotators will then give their preferences for each of these instructions, and you end up with this data set of instructions and two responses for each instruction, and one of them is chosen. Now, given this data set, you could do many things. The simplest thing is to just, for example, continue training on the chosen pair. You could also train a reward model, which is basically a binary classifier which predicts if a given response is chosen or not, and then continue training your model using RL. And there's any number of techniques in between that you could use. Finally, you want to go through human evaluation. So the typical way to do this is you gave them same instruction to the model that you just trained and to a baseline reference model. And then you can report win rate over the new baseline model given human feedback. Okay, so what are the challenges here? Well, there's actually quite a high cost of feedback collection. So just for collecting 10,000 binary preference labels, vendors like Surge or Scale quoted us $10,000 to $20,000. And it can take days to weeks to set up this like human pipeline to actually collect this data. The second is a lack of reliable evaluation. So there's no standardized benchmark, like what instructions are we evaluating over? What sort of tasks are we targeting? And furthermore, the human eval is hard to reproduce. Your pool of human annotators not just change over time.
Yeah.
Oh, I think on Zoom, if you can mute yourself. Cool. Yeah. So the human eval is hard to reproduce, right? If you want to run the study again 6 months down the road, like if you have a new pool or distribution of human annotators, that can be quite tricky. And lastly, there's like a few validated implementations. The pipeline is pretty complicated. It's more complicated in supervised learning, and RL can be tricky. So our proposal was, why don't we build a simulator to be able to study this cheaply? And the goal was, let's see if we can transfer the scientific insights from simulation to reality. So in an ideal case, the pipeline would look something like this. We have a few different methods for how we would actually perform this learning from pairwise preference data. We could then train each of these methods in simulation. The simulator would then tell us, will give us a ranking, which method is the best. We could then take the best method and then retrain it on real human feedback before deploying it to users. Okay, so let's break down exactly what's going on in the simulation. So there's roughly 3 steps. So one, basically, instead of getting manual human feedback for each pair of examples, we will use API LLMs to provide this pairwise feedback. Then we'll use this data set to train our models. And we have a number of reference methods that we implement, for example, PPO, best of an expert iteration. And then given the new model, we'll again use API LLMs to compare it against the baseline in PPO win rate. And then this will give us an overall ranking that we can then use to rank the methods. Cool. So this is what the overall pipeline looks like. And going back to original motivation, right? We wanted to make this accessible, and we wanted to make this cheap to run. And this achieves exactly that. So running one of these experiments, for example, with 10,000 binary preference labels, takes $70 to query the API, and you can run it overnight, and is fully reproducible as long as the API endpoints don't change. Whereas for human feedback, it could take thousands of dollars, take days to run, and it's not reproducible if your pool of human annotators changes over time, which is the more likely scenario. Okay, so how do we actually measure success of the simulator if we can build it? Well, we imagine like two parallel universes. So imagine in one universe, you train and evaluate only with human annotation. So this is a world where you only care about deploying on human data, so you only train and evaluate on human data. This is kind of like the gold standard. The second is you train and evaluate the method only in simulation. So in this case, you have no access to any human data. What we want to do is measure the correlation between these human and simulation environments and test if other sort of qualitative insights transfer. Cool. So this is a sneak peek, but overall the simulator is pretty reliable. So what I'm plotting here is each dot is a different method. For example, PPO, best of n, expert iteration. On the x-axis is what if we take that method and train and evaluate it only in simulation. This is trained on simulated data and evaluated with the simulated annotators. And this gives us a simulated win rate. On the y-axis is what if we take that method and train it only on human data and then evaluate it only on human data. And then you compute the win rate on the y-axis. And overall, we can see that there's a fairly high correlation. There are some model flips, ranking flips, which I'll talk about. But overall, it does give us confidence that improvements in the simulator can transfer over to the real world. Okay, so let's break down exactly how we did it. There's roughly 3 steps. Designing the synthetic preferences, which is by far the most important, creating the automated evaluation, and then benchmarking a few different reference methods. Okay, so let's talk about designing the synthetic preference. So if I were to tell you to do this, a few of us are pretty seasoned LLM prompting experts in this room. How would you go about doing it, right? The task is you have an instruction and you have 2 responses and you want to know which one is the better one. Well, the baseline is like, why don't we just prompt it a GPT-4? Maybe we give it a few in-context examples and ask it to judge which one is the better one. So that's what we started with. And that's what this plot shows. So on the x-axis is the cost. So the single GPT-4 point, is about an order of magnitude cheaper than actually querying humans for the preference data. And on the y-axis, we measure agreement with the human mode. So this is if I take 3 held out humans and I compute their human mode. Again, this is a binary task. And then I compute the agreement of either GPT-4 or a 4th human with that human mode. So GPT-4 gets about a 65% human agreement rate, which is not great for a binary preference task, but the data is pretty noisy. And if you look at the human baseline, it's 66%. So looking at this data, you might think, oh, that's pretty good. It's cheap, it's almost as good as humans. Why don't we use it? Well, the issue is that humans have actually pretty high intra and inter annotator variability. And the single GPT-4 annotator lacks this. So what do we mean by this? If I ask 2 different humans, which response is better, A or B, they're more often than not likely to disagree on this rating. And not only that, if I ask the same human, but maybe a few days down the line, they also have a high chance of disagreeing with themselves. GPT-4 doesn't really exhibit this. If you ask it, it's almost deterministic. I mean, the only reason there's a little bit of randomness here is because we changed the order of the 2 responses in the prompt. But its variance is actually pretty low. Okay, so how do we fix this? Well, the solution is kind of simple. We can randomize the annotators. So we introduced inter-annotator variability by randomizing over 13 different prompts and models. So what does this mean? This means that we ask the model to output in either JSON mode, XML mode. We tell it to pay attention to length or factuality or lists, or we change the underlying baseline model. So instead of GPT-4, we use text-to-Vinci 3 or GPT 3.5. And then to introduce intra-annotator variability, we randomly flip 25% of the preference labels. Okay, this sounds like, maybe especially this intra-annotator variability sounds like a strictly suboptimal thing to do. And we'll see exactly why in a second why this is necessary. But looking back at our previous plots here, we can see that at least on the variance spectrum, the variance for these new annotators has significantly increased and is much closer to the human line, the human blue line. Cool. Okay, so this slide is sort of like the real reason why faithfully modeling the human preferences is really necessary. So when doing any of these RL experiments, there's a phenomenon known as reward model over-optimization. And this is something that not only we notice in our human experiments, but other studies and other human studies, such as those done by OpenAI, have also noticed as well, which is that the proxy reward poorly estimates the true human reward. And this means that it's easy to overfit on this proxy reward. So, okay, so what is exactly does this all mean? Let's take a step back. So in this plot, this is like human preferences. So this is completely in the human universe. I'm training on human data, and then I'm evaluating with real human annotators. And on the x-axis, I'm measuring proxy reward. So with any of these RL methods, you first train this reward model, and then you optimize against this reward model. So the proxy reward is the reward given by this reward model that you trained first. So as you can see in this plot, up to a certain point, optimizing against this reward model is beneficial. You do increase your true human win rate. But after a point, you start to decline for PPO, both PPO and best event, and expert iteration kind of plateaus. This means that after some point, you start to overfit to that reward model that you've trained, and you're no longer making progress on the true task that you care about. And this is a pretty robust phenomenon seen in most kind of human feedback studies. Okay, now, if we look at that single GPT-4 annotator, that simple baseline that we had talked about at the start, that behaves extremely differently. So again, in this plot C, this is completely in the simulated universe. So I'm training on synthetic data. Then I'm measuring this proxy reward on this reward model trained on synthetic data and evaluating it with a synthetic annotator, with a simulated annotator. And what we can see is that there is basically no over-optimization happening. As you keep optimizing the proxy reward, the win rate, as determined by the synthetic annotator, keeps increasing. Now, you might look at this and say, hey, that's great. We can just keep optimizing the proxy reward and our numbers keep going up. But remember, we really wanted to faithfully mimic the human reality so that we could understand what techniques and algorithmic improvements would transfer over. So this definitely looks very different than that. But also B, like more practically, it's just really hard to do any hyperparameter optimization here because the performance of your method is only bounded by how much compute you allocate it, which is not true in this case. Cool. So now if you look at sort of our new synthetic preferences that I've introduced the intra-annotator variability, they actually look much closer to the human reality. So again, this is completely in simulation, trained on our synthetic preferences and evaluated with our simulated annotators. And as you can see, we get that telltale reward model over optimization. And sort of the method rankings also roughly follow each other, which is nice to see. Cool. Okay, so next is automated evaluation. So for this, we kind of just reuse the 13 synthetic annotators that we had, this time without the noise. And we measure the pairwise evaluation by measuring the win rate against our baseline here was DaVinci 003. As for the set of instructions, we collected a bunch of open source instruction following datasets that existed at the time. And now the key question here is, are these datasets really representative of what we care about when interacting with a language model? Now, luckily, we had actually deployed the Alpaca demo for a few days. And so we actually had live user instructions that people had entered into the chatbot. And while we weren't able to release this data, we were able to compare some aggregate statistics over it. So what we did is we simply compared the win rates across our aggregated data set of Alpaca farm on the x-axis and our demo instructions. These are the real live user instructions on the y-axis. And you can see that there's actually a very tight correlation between the two. And this means that making progress, we can have fairly high faith that making progress on our aggregated benchmark actually makes progress towards real instructions that people actually want to use with our chatbot. Great. And now let's talk about sort of benchmarking results. So, one of the original questions we had is like, okay, let's try and demystify each of the pieces of this pipeline. We went from pre-trained to supervised fine-tuned model to PPO, or any of these RLHF methods. Which ones actually help and how much do they improve? So clearly off the bat, we can see that going from the SFT model, the step 1 model, to the PPO model that uses this RL technique, it gives about a 10 percentage point gain in both the simulated and the human win rates. So that's a pretty clear improvement there across the board. You can also see that the pre-trained model is pretty hard to work with. It kind of scores pretty lowly on this because it really just can't follow the instructions. And so jumping from the pre-trained to any of the SFT models is actually a pretty huge benefit in of itself. Finally, we can even understand the method rankings between different types of learning from human feedback methods. And one of the most popular kind of debates that exist online today is PPO versus DPO. PPO is probably the most widely used, but DPO is a very accessible alternative that more open source folks have been using. And as you can see, this is actually DPO we implemented later down the line after we had released this study. That's why the human win rate does not exist, because again, it's not a reproducible pipeline. But luckily, we could plug it into our simulator, get the simulated win rate out, and it actually performs just as well as PPO. So that gives some credence to the fact that maybe these methods actually do perform very similar. Cool. And then it's always good to look at model output, just as we did last time. So in this case, if I ask a simple question, what are the 5 most common causes of stress? Just the step 1, the simple alpaca model will tell us, work, money, relationships, health, and family. You can't go really go wrong with any of those answers. And then if you ask the alpaca plus PPO model, wow, it'll give you a lot of text, right? It'll put stuff nicely in the list, and it'll expound on each of these. And this is actually definitely something we realized when training, or when training our PPO models or training any of these methods with human feedback, is that one of the primary statistics that they pick up on is detail and length. A detail, length, and sort of how well formatted and is it in lists. And so this is one of the primary effects that we saw. And so if you've ever played around with ChatGPT or GPT-4 and you're like, wow, this is extremely chatty, because it's gone through a very similar pipeline and has picked up very similar sort of tendencies. Cool. So that was all sort of in simulation, in the alpaca farm simulation. We could take some of the primitives, like the evals primitives that we had built, and we could just use them standalone to evaluate the quality of instruction following models. And that's exactly what we did. So we kind of took out those primitives, those internals, and we made alpaca eval sort of standalone automatic evals package. And sort of this has really helped sort of improve benchmarking on general form instruction following by the community. So we've had 100+ models contributed by the community. At the time when we released this, alpaca was at a 26% win rate. Within 6 months, we had new open source models had reached 83% win rate. And Yanni even pushed an update to alpaca 2.0, which is it's a whole different set of things. And the really nice thing about this is that all these evaluators are kind of backed by the alpaca farm data. So for each of these evaluation methods, and as new models come out, we've been updating them to new evaluation techniques. We can always compute the human agreement because we have the real human data. So we can compute the human correlation. And we can even compute the Spearman and Pearson correlation of the system level rankings in our original simulator plot. So this is additional validation for why some of these instruction following automatic evaluators might be useful. Though they are sort of reaching their end of life nowadays. Cool. Apart from that, it's also been great to see just synthetic data pipelines being adopted more broadly. So many open source post-training datasets these days incorporate synthetic data recipes. For example, OpenHermes, UltraChat, UltraFeedback, and Wizard-LM. There's even been some work on scaling up synthetic data up to billions of tokens and training really small models called Phi3. And we've also done some work on, you can apply, some similar synthetic data techniques to training models in the visual domain as well. So CLIP, for example, is a model trained on image caption pairs. What we saw is that many internet data sets like YFCC and CC, they have very poor internet captions. The captions often don't even correspond to what's going on in the image at all. So one really simple thing you can do is just take, an image captioning model. In this case, we took Blip, and use it to generate a set of captions for CLIP, and then use that to train a better CLIP model. And as you can see, for example, for YFCC, we see a mean, downstream transfer accuracy of 35% to about 55%, which is pretty big. Much less so for CC, and sort of this doesn't exist for Cocoa because that's a human-written data set. Cool. So yeah, so I've talked a lot about building these synthetic data pipelines. It's always good to take a step back and think about what the long-term implications of this might be, especially as we deploy these models more and more often. And one thing that we're seeing is that it is actually important to consider and explicitly model some of these deployment time feedback effects. That's what I'll talk about next. Right. So at the beginning of the talk, if you remember, I mentioned that we're deploying these models more and more, and a lot of these traces of how users are interacting with these models are ending up back on the internet, which is serving as our sort of data source to train the next iteration of models. So to give you some examples, Stack Overflow actually had to ban AI-generated answers on their site because they're getting overwhelmed with them. And this is actually a little bit concerning because Stack Overflow is one of the primary sites that we use to scrape and train our models on code data. There's many blogs, about ChatGPT blogging now. And this one random article about someone winning a state fair prize using Midjourney AI kind of just blew up. And now this image has been replicated, this generated image has been replicated, who knows how many times across the internet because of the reporting on this. So these effects are very real. And it begs the question of, is this something that we need to be concerned about? So, right, so is this bad? Like how should we think about this? Well, what do we know, right? We know that models can amplify certain biases. So there's been prior work on this in both the image classification and language modeling settings. So we know that models can at test time amplify gender bias, toxicity, and demographic stereotypes. On the other hand, there's a long line of work on semi-supervised learning and self-training, which shows that the model can actually improve when training on synthetic data or synthetic data that comes from the same model. So what's going on here? How do we actually disentangle these two? Well, our goal is really to understand when and by how much do these model biases amplify under feedback. So we need a new setting. We need a new setting to study this because this hasn't really been studied before. So we propose this new setting called data feedback. And the way it works is very simple. You have, I'm just gonna start with like a very simple image classification, binary image classification example, just so it's easy to grok. But you start with the data set, at time t, that's, as a result of the internet. You train a model and now you deploy it. And then between time steps, two important things will happen. We'll continue to get new like human generated, human annotated examples. At the same time, we'll also continue, some of the users will actually interact with the model. And so we'll get some fraction of model generated outputs as well. And these will be added into sort of the internet data set at time t. And then all of that will be used to retrain the new model at time t as well. So this is the new setting that we considered. And actually, it's really important in this setting to really consider this internet data source as aggregating information over time. That is, it's accumulating this information, use samples over multiple time steps. There have been some later works that study this similar sort of setting, but they actually don't consider data aggregation. And the takeaways can look very different if you don't. So this is an important point to consider. Cool. So let's go through exactly like what can go wrong in this very simple data feedback set. So, say we have this task of, given male and female healthcare workers, pictures of them, we want to classify if they're nurses or doctors. Well, suppose that our initial model that we have trained has some bias. This gender bias has been shown to already exist. So it's pretty plausible to think that, maybe for female healthcare workers, it biases towards labeling them as nurses instead of doctors. Well, now when users interact with this model and these outputs are uploaded online, so this will end up in our data set for the next time step. And meanwhile, we will also continue to get like, true human annotated and tag examples as well. And both of these sources of data will combine to add up to a new data set, just straight from the internet. And because this data set is now even more biased than the previous iteration, it could be that the resulting model kind of amplifies its bias along that direction. Cool. So, okay. So how exactly can this happen in practice? Like what types of models, which types of models can this sort of bias amplify? Well, like continuing with this example, let's imagine for in this case that it's really hard in this data set to tell if a female healthcare worker is a nurse or a doctor. Say there are some contextual cues that are simply not present in this data set that the model needs. And so in this case, like what is the Bayes optimal thing to do? Well, if the majority class is nurse, the Bayes optimal classifier is actually to predict that every single image is nurse. That's how you like achieve the highest accuracy. Now, but what happens if you do that, right? That means all your model annotated examples at the next time step are going to be 100% nurse. And that means when you add it to your data set, you are skewing the gender bias even more aggressively towards one that already existed. Okay, what is the alternative? Well, what if you train a good sampler? in this case, it may be suboptimal. It may not be like, the optimal thing to do, but, let's hold a little bit of disbelief for a little bit. But if we could train this good sampler and deploy it, well, then this model would simply replicate the data statistics that it was trained on. And in this case, it would continue to label, 2/3 of the outputs as nurses. And this would, maintain the gender bias in the data set over time. Okay, this might be a little bit contrived. Let's see how this is actually, how it could be used in practice. So in this case, we ran a language modeling experiment. So in this case, we trained GPT-2. And what we did is we gave it a few prompts, asked it to complete the rest of the paragraph. And then we iterated over time. So we ran a number of feedback rounds. So you can see we ran from 0 to 15. And concretely, the bias we're going to measure here is the repetition rate, because that was the easiest thing to measure on for GPT-2. And you can see the model, when you generate via nucleus sampling, it's very interesting. When you generate via nucleus sampling, the repetition rate of the model is very low. And it stays extremely low throughout this feedback cycle. But when you generate via beam search, the repetition rate is very high, and it quite quickly explodes quite after that as well. And the reason for this goes back to the previous slide, right? Nucleus sampling is an approximation to sampling from the true model's conditional distribution. And if we believe that sampling provides stability, then this is the sort of result that we would expect. Versus beam search is an approximation to the most likely sequence from the model. And again, if we believe like sort of like the hypothesis or like the example on the last slide, then when we train, for something that looks like beam search or getting the most argmax prediction, things can get unstable pretty quickly. Okay, so this kind of begs the question: is there a way to fix this beam search model? Is there a way to have a model that still outputs like the argmax, but does not, sort of amplify so quickly over time? So this is sort of a rough mental map of where we're at, right? We've seen that, for example, like argmax prediction strategies, we've seen two strategies that are both feedback unstable: Bayes optimal models and beam search LMs. Whereas for sampling strategies, we've seen that they're feedback stable, and one concrete strategy is nucleus sampling LMs. Now, where we'd like to be is in this like bottom left corner here. This would be the sweet spot. Like, is there a strategy that both argmax samples and is feedback stable? Well, we don't have to worry about this. There's actually been some prior work showing that interpolating classifiers, shown by Nakran and Bonsall, fit exactly in this bracket. So okay, so what exactly does that mean? So they theorized and showed experimentally a conjecture called distributional generalization, which is that if your classifier is interpolating, then sampling or like choosing the argmax of your model's conditional distribution is roughly equivalent to sampling from the model's conditional distribution in expectation over your data set. And this holds for interpolating classifiers. So concretely, here's an interpolating classifier experiment. So this is like CFAR, and I've imbalanced the data set to have a lot of dogs. And in this case, we might be concerned that the bias is we predict too many dogs over time. And yeah, as you can see, when running this experiment under data feedback, again, this is the number of data feedback rounds. This label prediction bias actually barely increases over time, even though this model, this is an image classifier, so this is operating under an argmax prediction strategy. So even though that's the case, the feedback dynamics are relatively stable over time. Okay. So is there a way that we can leverage this intuition to fix our like beam search model? Can we leverage the intuition that interpolating classifiers behave like samplers? The answer is yes. What if we try and interpolate the language model? That's exactly what we did. We overfit the GPT-2 model slightly, and it actually pretty drastically resulted in a decrease in the repetition rate over time. So you can see like that's sort of the effect of the intervention. Now, of course, you do make some compromises on the quality of the model. For example, its a diversity score and other things like that go down. But this at least provides us or gives us a different knob to think about how we make trade-offs when considering potential feedback effects, and gives us another knob to tune this diversity trade-off. Cool. The last question we might have is, okay, well, we came up with this new setting. We did some experiments, but can we actually provide any guarantees? Like, how do we know these experiments will continue to hold? And the answer is yes. This is the only slide with any theory, so just hold on for a little bit. But okay, so let's say that our model bias is just measured as some function of our model's predictions. So we will say that we can have a model, or we can have a learning algorithm that is stable if it fulfills this uniformly faithful condition. This is another way to say that this model behaves like a sampler, but essentially what this means is that if I train this model on this data set, then the difference between the data set bias, which is this term here, and the test time prediction bias of that model is less than delta for all joint distributions with this specific marginal. Okay, so that's the precondition. And the resulting theorem says that, okay, if we have an algorithm that is uniformly faithful like this, then under the data feedback setting, for all time, we're going to look at this quantity. And this quantity is going to be very similar. It's going to be this quantity here is like the difference between the bias of the base distribution, and this is going to be the bias of the model at time t. The test time model, the test time bias of the model at time t. And that we can actually upper bound by this sort of time dependent upper bound. So it's function of m, k, and delta. And if you saw like the orange sort of theoretical lines on the previous plots, that's exactly where it was coming from. Now this is a bit hard to look at. So simplifying it, we get this time independent bound, which is m plus k over m times delta. And this makes a lot of sense, right? So if you remember, m was the number of examples that were human labeled between each time step. So if m goes to 0, then this quantity kind of blows up and your bound becomes vacuous. And otherwise, you can sort of control the rate by how much delta penalty you pay between each of these time steps by controlling m and k appropriately. Cool. So yeah, so I'll take a moment to recap now and just talk about some future directions that I'm excited about. So we saw that these model-dependent data pipelines. So there are a few challenges with these new sort of like LLM pipelines. One is that we have these model-dependent data pipelines. They are costly and they're hard to reproduce and do science on. So one technique that we saw is the synthetic annotators provide kind of useful feedback data that we can use to construct a simulator and study these effects. The second is that it's really hard to evaluate open-ended generation. So Alpaca Eval provides some automatic evaluators that are correlated with human judgments. This is at least a step in the right direction, although there is still a long ways to go. And finally, the deployment of LLMs creates potentially unwarranted feedback effects. And we saw that data feedback at least provides some initial theoretical understanding and practical mitigation strategies. Cool. So future directions. So I'm actually quite excited about, further scaling synthetic data pipelines. I think especially for vision language models, they're quite needed. High quality image caption pairs and video caption pairs are kind of small in number on the internet, and they're very hard to come by. So some of this initial work that we've been doing with Zane is, recaptioning web vid using ChatGPT, and that's shown some promising results. For example, like the experiment I already mentioned is recaptioning CC using Blip, and that has shown some promising results as well. Another direction I'm pretty excited about is more grounded topic-specific evals for open-ended generation. I think there's many things to do here. There's many things we care about, many tasks we care about, many aspects of generation we care about, and getting a way to do this reliably while still being open-ended is a really big challenge. And some initial work I've done here is a vision language benchmark, instruction following benchmark that I think is more flexible than ones that previously existed. And I think the last thing is like more experimental study of data feedback effects. So there's the data feedback model we presented is actually pretty simple. You can imagine this pipeline being so much more complex. If you allow covariate shifts over time, if you allow multiple models in the mix, if you allow different distributions of human labeled and like model labeled examples coming in over time. So there's like a lot of work to be done there, and this is just what we did is just very initial. Cool. I guess this is a good time for questions. Yep. Oh, go ahead.
Fair. I'm wondering, can you just comment on if instead of sampling from the Bayes optimal distribution, like there's like some fairness constraints where a lot of the platforms are implementing. So would you get into this amplification effect where there's maybe like fewer and fewer male doctors? Or like, does it stay stable? Because humans can still keep giving biased human judgments.
Yeah.
While then models might have to overcorrect their synthetic outputs. What are your thoughts?
I see. So you're saying basically the bias is coming from like there's more bias coming in from the human label samples rather than like the samples that the model is producing.
If so.
Yeah, yeah. I think in that case, I think that case is really interesting. Like in that case, I mean, it's sort of like the quantities kind of act in the opposite way, like the model generated samples, because they have this constraint or maybe the stabilizing effect, right? And the human generated examples are sort of like the ones that are like veering it off distribution and like causing it to be more more biased over time. I mean, the thing that's really interesting there is like with any of these mitigation strategies, you always like lose performance, right? If you want to enforce this fairness constraint, now you're giving up some model performance in order to enforce that. So I think developing more mitigation strategies along the lines would be very useful, because even if you're still enforcing the fairness constraint at the end of the day, if your model just natively matches that, then you don't need to take that additional sort of like utility hit. Yeah.
If that's something that the last example you showed, I guess the sort of best case scenario is just sort of like the facts that are in the data. And I feel like there's also a sort of parallel kind of attitude of like, oh, like synthetic data is somehow going to get us like self-improving models, and like we can use synthetic data to do better than the last generation of model. And like, I'm just curious what you make of that, like intuition or like proposition, and like how should we think about like what can we extract from synthetic data? Like, are we just going to be limited to whatever we're distilling from, or like can we actually use this to improve the model? And if so, like how is that possible?
Yeah, I think that's a good question. I mean, I think the thing to think about is that these synthetic data pipelines don't really exist in a vacuum. Like, there's always some additional signal that's injected in the process along the way. So either that's like, just like the prompt distribution that you're using to sample the synthetic data from, that's really important. Or like, you have additional heuristics that go on top of it, or other filtering pipelines and things like that. So I think all of these ways are other ways we can inject information into the synthetic data process. Now, it does make it very hard to study because there's so many complicated levers that you can pull. But I do think that like the limit there is not really like, oh, like we can never get past the best model that we have currently, but it's like the limit is like more like our creativity and like sort of the pipelines that we can create. Yeah.
Great talk, like I really enjoyed it. What do you think are the biggest limitations of evaluation right now, and like what do you think should be like fixed going forward? Can we like evaluate very strong models as well, or something, if you have any thoughts?
Yeah. Yeah, it's a tough question. Like sort of the only way we really know how to do open-ended evaluation automatically is with using like a strong model. And so you start to hit these limits, right? Like if you already have like a really strong model, like how do you evaluate it? It's actually not clear. Like, I mean, there are cases where like coding or math where you have like some more grounded eval that you can run something against. Like in those cases, you can provide a lot of signal, but otherwise it can be like pretty hard to ascertain. I think one direction that's interesting is like, can we just break down overall eval into like more fine-grained variables like factuality or detail or grammar or things like that. And maybe that makes the job of evaluation just a lot easier. And so yeah, that's one way to scale the pipeline. But yeah, I don't know. I think that's a good question. Yeah.
Make sure we have time for your knowledge.
Oh yes. Okay. Cool. I'll do my acknowledgement. So yeah, I wanted to thank my committee that's here today. So Chris, I'd like to thank you for chairing. I also think that I came in not being an NLP person, and I think the NLP group was always very inviting and welcoming and warm, and I think that's really where I found my home for the past 4 years. And you had honestly like a huge part to do with that and showing up to all the lunches and everything. So that means a big deal. So thank you for being here. Michael, yeah, I mean, it's been really great to work with you in this past year. I think we worked on like, a couple of very interesting projects together. And I think your perspective has always been very unique. And so that's something, yeah, that I really appreciated and valued working with you. Oh, yeah. Yeah. I mean, Percy, it's been really great working with you. Even though I'm not really officially advised by you, always been talking pretty regularly. And that source of opinion has always been very valuable. And especially with the last year, things got hectic with doing the startup and then coming back, and you were kind of a grounding voice in that. So thanks. Okay. Yeah, and then lastly, I'd like to thank Ludwig. Yeah, I mean, Ludwig, I mean, we've been working together for many, many years now, and you sort of set me down my like experimentalist path, and so I owe a lot of like those roots and those beginnings to you. And yeah, I'm extremely excited to work with you now again at Anthropic. So yeah, looking forward to that. Oh, just a skip over. Yeah, Tatsu, I honestly can't think of a better advisor to have for the past 4 years. I think you very, very kind and understanding. And I think, especially at the beginning, like you were starting up as a faculty, I was, one of the first batch of students, and like the amount of time you spent with me was really, really great, especially during COVID. And yeah, I think that just contributed to a lot of my own like personal growth and development. And I remember how much time we took apart away from research, like discussing not research stuff. Like we spent like a whole 6 months, I think, discussing like philosophy of science and like I don't really know if I have anything concrete to say other than like, my views on peer review have been quite radicalized now, but um, I do think because of that, I've gained a lot of confidence in the specific research taste that I've grown, and I think that's one of the best gifts that you can give a student. So yeah, thank you very much for that, and yeah, it's been great. Cool. I also want to thank a few of my close collaborators. If you're on the slide, yeah, I've worked pretty closely with you over the past 4 years. And I want to just take a moment to acknowledge all of you. Like a lot of this work is just, it's definitely not all of my own. Like a lot of it is, most of it is like really like done with everyone else, and like everyone else has had more contributions than I have on it, pretty honestly. So, just want to take a moment. I think especially Tianyi, Yan, and Chen, I think I really found my stride in my PhD in the last year and a half, working with you, with the three of you. And yeah, I just want to say it's been a very, very fun, and I hope I find a group like that again to work with. I think that's very special. Cool. There's also many, many other people I'd like to thank in Tatsu's lab and the NLP group, and just beyond. So I just attached a couple pictures that I found on Slack, like 10 minutes before this talk started, and a list of names of people that I've talked to over the years, and I've really increased my worldview, and I'm very thankful for that. Yeah, last thing, I feel like I feel like we've captured a good culture in Tatsu's group of and I feel like we should continue down this route. So this is one of the first reading groups I ran of just making bets on where GPT-3 and 4 was going to be relative to GPT-2 and 3. And I heard from Zitong that there was a new version of this reading group done last week, where there was bets on GPT-4 and 5. So I'm very happy that tradition is continuing. Yeah, just a few last acknowledgements. I'd really like to thank my family. So my parents are here. I think my brother might be on Zoom as well. So yeah, I mean, they've really been my rocks throughout this process. Yeah, I really wouldn't have been able to do it without them. And it's been yeah, been super great. I also want to, shout out to Mira. I know how hard med school can be, and especially, doing long distance, like time zones don't always match up and things like that. But you like saved me countless times, and I can't imagine doing it without you. And as I said, I was putting these together 10 minutes before this talk began. So unfortunately, this last slide didn't make the cut. But I thought yeah, these are some group chat names that a lot of my friends and I are part of. So Team A Patal is our volleyball group chat, for example. So very very happy to be a part of that. And I think, yeah, I mean, I think, honestly, like in the past year and a half, like I feel like I both found my research stride and also like, for those of you close to me, that like I'm going through, some health issues right now and like got a pretty major surgery coming up soon. So I feel very lucky to, have this group of friends to talk about that with and go through that with. Cool.